Today's problem, maximum sum combination difficulty, medium accuracy, it's almost 50%. That's surprisingly high. I mean, I say that now. At first I thought it looked like a very easy problem, but I don't feel that way about it. I don't feel that way about it now. Average time 30 minutes. That's pretty high. You are given two integer arrays, A and B, of equal size. Sum combination is formed by adding one element from A, one from B, using each index pair I, J at most once. Return the top K maximum sum combinations sorted in non-increasing order. All right, so here's a couple examples. Array A is 3, 2. Array B is 1, 4. What are the maximum sum combinations? Well, 4 and 3 is 7. 4 and 2 is 6. Those are the maximum sum combinations. K is 2, so we only need 2. Here's a couple more arrays. In this case, K is 3. What are the maximum sum combinations? Well, you have 6 and 4 is 10. You have 6 and 3 is 9. You have 5 and 4 is 9. Constraints. Array sizes are between 1 and 10 to the 5th, 100,000. K is between 1 and the array sizes, and the numbers in the array are between 1 and 10 to the 4th. Expected complexities, n log n. Because we're going to want to do a sort, I think my problem here was I didn't pay enough attention to the time complexity. Topic tags, sorting, and heap are the ones that stand out there. All right, my first thought was, well, this is very simple. We'll just take all the possible sums and put them in a max heap, and then pull the K largest elements off the heap, and that's it. It doesn't work because there's a fairly late test case that results in a heap overflow. Either the numbers are too big or there's too many of them or both, but there's a heap overflow. So that doesn't work. My next thought was, let's just not keep the heap once the size, let's not keep any more elements in the heap once the size gets to K. So with a max heap, that would mean we're not going to put anything else in the heap if the smallest element is larger than the element that we're about to put in. Smallest element in a max heap would be the last element in the heap. It's not easy to access the last element of a priority queue. It's easy to access the first element, but not the last element. So then why not try a min heap? It's really the same thing. It's just we're going to have to reverse it at the end. But okay, so we'll do a min heap, and then we can compare the first element in the heap, which is the smallest element, with the element that we are about to add to the heap. Once the heap reaches size K, and if the element is not bigger than the smallest element in the heap, then we're just not going to add it. The heap never gets larger than K, and it never overflows. Right? I tried that and it timed out. And I guess, I mean, in hindsight, I should have thought through this a little bit more clearly, but to enumerate all the sums of these two arrays is going to be n squared, not n log n, right? So we are about to try a new approach that I hope eliminates duplicate computations. We'll see how it goes. I'm going to move this over here. And what do we have? Well, first we'll just keep n as a length variable. Sort the arrays. Sort A, sort B. We don't want them sorted in ascending order, which is the default. We want to sort it in descending order because that way we're going to get to the maximum sums first. All right, so there is a reverse method here that just reverses the array. So now we have arrays sorted in descending order. We've got a priority queue of integers. What is in, I'm sorry, of integer arrays. What is in there? Well, what's in there is the sum of two elements, also the index, the index of array A and the index of array B. Those are the two numbers that we added to get the sum. We've also got, can I scoot this over, a comparator here, like, well, how do we decide based on these three element integers which one is the max, which we need to know for a max heap? Well, okay. These are the two arrays, and the maximum array is found by subtracting the first element of the second array. I'm sorry, subtracting the first element of the first array from the first element of the second array. Now, the first element, as I said, is the sum. Now, doing it this way, y minus x rather than x minus y, puts the largest element at the front. All right, hash set. We're going to keep track of computations that we've already done. All right, we're going to put the first element in the max heap. Now, the maximum sum, because we have these arrays sorted in descending order, the maximum sum is going to be the sum of the first element in both arrays. So here's the sum, A0 plus B0, and here are the indices, 0 and 0. And we're going to add this. The format of this is not really important. It's just important that we get into the set that we tried these indices, A0 and B0. Okay, so we're not going to do them again. We're going to define an array list result that is going to contain our result. All right, let's see. Okay, so we are going to proceed here until the result size, well, as long as the result size is less than k. Now, we should get these numbers in decreasing order. We should get the biggest numbers first, and so once we get to k numbers, we can stop. We do want to make sure that the max heap is not empty. That would be bad. But each time through the loop, we are going to pull the top element off of max heap. We're going to get the first. Now, max heap, again, contains integer arrays. The first element in the array is the sum. The second element is the A index, and the third element is the B index. And we're going to add that sum to the result. Now, this doesn't really line up, does it? Now, what's the next biggest number? Well, if we think about this, starting from the beginning, but it really works for any I and j index. The first number that we put in there is the index of array I. I'm sorry, the index for array A was 0. We'll call that I. The index for array B, we'll call that J, was 0. The next biggest number is either A0B1 or B0A1. In other words, it's either I plus 1J or J plus 1I. So let's take a look here. I mean, we'll consider both of them. If I plus 1 is still within the array range and we have not visited this combination of numbers before, we're looking in the set, then we will add a new integer array, and that is A at I plus 1 plus B at J, and the indices, I plus 1 and J. We will add that combination to the set, to the visited set. We will also consider j plus 1. If j plus 1 is still within the bounds of the array, and we have not done this computation before, we will add a at I plus b at j plus 1 to the max heap along with the indices I and j plus 1. We will add that to the set. Now, once we get the 3 maximum numbers in the set, we're going to stop. Once we get the 3 maximum numbers into the array list, I should say, to return, we're going to stop. So we're not going to go ahead and work through every possible n squared combination of sums. All right. So let's try this. All right, good. Well, you can see that I've tried and failed on this a number of times, as I already mentioned, but it's a little bit well. I mean, they kind of give it to you, if you're paying attention. The time, the runtime is not intended to be n squared, so you probably won't have time to go through and compute every possible sum, every possible combination of the two arrays. That what you want to do is sort them in descending order, and then proceed through the arrays in such a way that you get the maximum numbers in order. And once you get them, you just stop. So that's it. Please give the video a like. You can subscribe. Click subscribe. You'll get problems of the day in your inbox every weekday. And we'll see you next time.